This section introduces cohomology through a single idea. Every cohomology theory measures one thing: the failure of a functor to stay exact. Feed a short exact sequence through a left exact functor, F. It preserves injections and kernels, but it loses surjectivity at the far end, and what leaks out there is an invariant, genuine structure rather than an artifact of the process. The derived functors, written RIF, are precisely that leak, graded by degree. The whole move of the introduction is subsumption. De hum cohomology, yet cohomology, sheaf cohomology, the extension problem for groups and modules, a whole zoo of ad hoc theories collapses to one primitive, read through different choices of F. Sheaf cohomology becomes the running instance because right derived functors fit it cleanly. The generative rule is simple. Name the functor, and its inexactness names the theory. This section explains why every cohomology is an obstruction promoted to an object. Start with the central move. A functor that ought to carry exact sequences to exact sequences typically carries only part of one. Surjectivity fails at the end, and the derived functors, written capital R, superscript I applied to F, are exactly the organized record of that failure. This one construction subsumes the ad hoc homologies under a single roof, holes in spaces, and the extension problem, the short exact sequence running from 0 to a 2b to c to 0 in groups and modules. Each one measures how far a map falls short of exactness, and the shortfall is itself the invariant. The introduction's whole promissory note is unification. Sheaf cohomology, Ye cohomology, and Derived cohomology all become instances of one construction, the same idea seen from three sides rather than three separate inventions, with spectral sequences computing the invariance by successive approximation. Everything after this is elaboration of a single sentence. Failure is structure. This section explains how an entire book's worth of linear algebra gets rebuilt from arrows alone. Every object here is defined by its arrows, never by its interior. A set, a group, a space, all become interchangeable once you look only at the morphisms going in and out. The chapter has a single move. Keep stacking structure on that arrows, only substrate until ordinary linear algebra becomes expressible without ever naming an element. The first layer is additive, where each home set is an abelian group, composition is bilinear, and there is a zero object. The second layer is abelian, where every morphism owns a kernel, and a cokernel, and a crokernel, and a kernel, and a crokernel, and a crokernel, and morphisms and epimorphisms are exactly those. The abelian category is the destination, the smallest arena general enough to host kernels, quotients, exact sequences, and so the derived functors the book is really after. What matters here is not the terminology. The point is building the stage that cohomology will later stand on. This section explains why homological algebra needs one particular kind of category before it can begin to measure anything. Before cohomology can measure anything, you need an arena where measuring is even a well-formed question, an arena where every map has a kernel, a cokernel, and whose epimorphisms are cokernels, which makes it abelian category, and this chapter's entire job is to lay the shortest track reaching it. Objects and arrows first, then arrows you can add, which makes the category additive, then arrows you can add, which makes the category additive, then arrows whose monomorphisms are cokernels, which makes it abelian. Everything the book does afterward, derived functors, sheaf cohomology, is homological algebra run inside such a category. The underlying space never reappears. Only its category of sheaves does. So this chapter supplies grammar rather than content. It fixes what the later verbs are allowed to act on. This section explains derived functors. Start with a functor that respects short, exact sequences almost. It carries the sequence 0 to a to B, to C, to 0 into a sequence that is exact everywhere except at the final surjection. That failure is not noise. It has a canonical, measurable defect. And that defect is the whole theory. The right-derived functors, written RIF, are exactly the correction terms that splice the broken image back into an infinite exact sequence. They continue the sequence onward. R1F of A leads to R1F of B, and so on without end. Here is the move that generates every instance. Do not repair the failure of exactness. Name it. The obstruction itself becomes a generalized cohomology. This single construction is what unifies ext, tor, and sheaf cohomology. The boundary predicts the rest. When F is already exact, all the higher RIF vanish. Nothing is lost, and there is nothing to measure. This section explains the derived functor and why the failure of a functor to be exact becomes the very thing you measure. Start with a short exact sequence and apply a functor to it. If the functor is only left exact or only right exact, one end tears. A term you expected simply vanishes. The derived functor is what falls out of that tier. It continues the truncated sequence into an infinite exact one, and each new term measures, degree by degree, exactly how far the functor sits from being exact. The failure is not a defect to repair. The failure is not a defect to repair. Ext, tor, and sheaf cohomology are one move. Seen thrice, the obstruction to exactness, read off functorially. This chapter builds that machine. It is where cohomology stops being a name and becomes something you compute. This section explains what a sheaf is and why the place it breaks is the whole point. A sheaf is the discipline that turns local implies global into an equality. You assign data to each open set, you add restriction maps, and then you demand that pieces agreeing on their overlaps glue to one and only one global piece. Drop that demand and you have a mere pre-sheaf where gluing can fail. The constant pre-sheaf and the exact one forms on the punctured plane are exactly where it breaks. That gap is no defect awaiting repair. It is the object the whole book is built to measure. A short, exact sequence of sheaves stays exact on stalks, yet loses surjectivity on global sections, and cohomology is the precise bookkeeping of what gluing forgot. The chapter sets the stage. The failure it stages is the plot. This section explains what a sheaf is. A sheaf is the exact bookkeeping of a single idea. The whole is nothing more and nothing less than its consistent local views. Start with a pre-sheaf. A pre-sheaf is a contravariant functor that assigns to each open set U a collection of data P of U defined on the open sets of a space X. Each inclusion of a smaller open set V inside a larger one, U gives a restriction map. So data is attached locally with no promise that it coheres. The turn of the chapter in chapter 3 is two axioms. Local sections that agree on their overlaps glue together into a single global section, and that global section is unique. Uniqueness kills redundancy. Existence guarantees assembly. That single condition is called descent, and it is the whole primitive. Everything downstream measures its failure. placed in the arc of the book. This is the object whose obstruction to gluing, its cohomology, will later count. This section explains how sheaf cohomology arises from the failure of one functor to preserve surjections. Start with taking global sections, the functor gamma that reads the sheaf's data over all of X. It preserves injections but destroys surjections. A map of sheaves can be onto locally, yet miss global sections because local solutions need not glue. Sheaf cohomology is the machine that measures exactly that loss. Write the ith cohomology of X with coefficients in F as the ith right-derived functor of gamma applied to F. The zeroth cohomology hands back the global sections, and each higher cohomology group is the obstruction to lifting local data to a global whole. This is the same move as ext and tor. A half. Exact functors, derived functors, quantify precisely what it threw away. Name. The functor's failure of exactness, and you have already generated its cohomology. This section explains sheaf cohomology at the structural level. So let me name what it measures before the machinery. A sheaf is local data plus a gluing law. Cohomology measures exactly how that law fails to globalize. This chapter is the derived functor machine of chapter 3 turned on a single functor, gamma, meaning take global sections. Gamma preserves injections but drops surjections. Its right-derived functors are sheaf cohomology, and degree P names the obstruction to extending sections across P-fold overlaps. H cohomology is the same measurement made computable from a chosen cover. It is combinatorial and hands-on, but skittish on wild spaces. Sheaf cohomology is the invariant version that always behaves. The move that makes the whole thing cohere is that they coincide when X is paracompact. The concrete shadow equals the canonical object precisely where the space is tame. This section explains what a spectral sequence is at the level of the machine that produces it. A filtration on a complex is a dial. It trades one intractable cohomology for a convergent sequence of approximations, each page the homology of the last. That is the whole engine. Hand it a filtered complex, and it returns E0, E1, E2, and so on, refining until the pages stop moving. At that point, the pages stop moving. The arc of the chapter is subsumption. Nech, Lire, Hochschild and Sarah, Kenneth, all of these fall out as instances of Grothendieck's spectral sequence, the derived functors of a composite, read off from the composite of derived functors, one machine. The named sequences are only where you aim it. This section explains the filtration, a single structural primitive. A filtration is a nested descending sequence of subcomplexes, a knob that stratifies an intractable cohomology into layers. Reading it off produces a sequence of answers. The page is written ER, where each page is the cohomology of the page before it. The differential shortens with every turn. Under regularity, the process stabilizes, and the limit is the sought cohomology itself, graded by the filtration. That is the whole primitive successive approximation made exact. Impose structure, then let a self-correcting sequence converge, trading one hard computation for a tower of easy ones. Grothendieck's version, relating the derived functor of the composite G after F to the composite of their derived functors, Rg after Rf, is the case that subsumes nearly all the other F to the composite of their derived functors. Rg after Rf is the case that long-lost the whole. This section explains why the derived category is the right place to work. Every resolution and spectral sequence maneuver in the book is a symptom of working in the wrong category. localize, invert the quasi-isomorphisms, the same move as forming a ring of fractions, and a complex becomes genuinely equal to its resolution, where before it was only resolved by one. In the derived category, D of A, the objects are complexes and the morphisms are spans. A span has a complex on the left, a complex in the middle, and a complex on the right, where the middle one maps back to the left by a quasi-isomorphism and forward to the right, and that backward quasi-isomorphism is inverted. Derived functors then stop needing chosen resolutions. They become ordinary functors on this new home. And the ith derived functor RIF applied to A is isomorphic to the ith cohomology HI of RF applied to A, which recovers the old ones. The payoff the chapter understates is this. Relations that demanded spectral sequences, like the derived functor of G composed with F, set against the derived functor of G composed with the derived functor of F, collapse to bare isomorphisms. This is Theorem 6.5. This section explains the closing move of the book, inverting the maps you kept apologizing for. Every construction in the book tracked resolutions. You choose one, apply the functor, read off cohomology, and paid for the choice with spectral sequences relating the answers. The epilogue ends the bookkeeping. You localize at quasi-isomorphisms, the same move that builds the rationals from the integers by forcing a class of maps to be invertible. Complexes, agreeing up to resolution, become literally one object. So a derived functor stops being a recipe and becomes an honest functor, RF. The tangled spectral sequence relations of the preceding chapter collapse to isomorphisms. R of G composed with F is isomorphic to RG composed with RF. The price paid for this cleanliness is exactness. D of A, the derived category, is additive but not abelian. Kernels are replaced by the cone. This section explains what an appendix really is. An appendix is common subexpression, elimination applied to an argument. It holds the lemmas. The main text leans on repeatedly push-outs and pullbacks. The snake lemma bears criterion that an abelian group is injective, if and only if it is divisible. These are hoisted out of the narrative's call path and proved once in isolation, so the cohomology argument never has to stop and prove its own plumbing. Everything here is a universal property or exactness, fact about abelian categories. The book keeps them at arm's length precisely because they sit below its altitude. The structural tell is this. What a text exiles to an appendix marks the boundary between what it argues and what it assumes. This section explains why the appendix earns its place. The main text runs on machinery. It never pauses to build, and the appendix is where that debt is paid. 3 tools serve one role. They are the algebra the cohomology silently assumes. Push-out and pull-back are a single universal property move, the most general completion of a corner, dualized across the opposite category, C-op. So one proof buys both. A snake lemma is the engine that turns a short, exact sequence into a long one. Every derived functor's connecting map is its shadow. Bayes' criterion collapses injective into divisible for abelian groups. This is the concrete existence claim that makes having enough injectives, and hence derived functors themselves, non-vacuous. These 3 are the ground the tower stands on.